Thanks. So good afternoon. I would first like to thank the organizer for giving me the opportunity to participate and present my work here. So today I'm going to talk about the entanglement transitions in integrable non-Hermitian flow case systems. So what I mean by this, I will going to explain. And this is work done in collaboration with my PhD supervisor, Professor Krishnendu Sengupta. So let us start. So first I'm going to describe the physical setup for the problem. So we have a closed quantum system, isolated quantum system. Then we are pumping energy to the system, and on top of it we are measuring, we are performing continuous measurement on the system. Now when we are performing the continuous measurement on the system interacts with the environment, and the system has a feedback from the measurement back action, and it results in non-unitary evolution of the system fields. So to model this kind of setup, one possible description is to describe it as an effective non-Hermitian Hamiltonian, and for the parameter regimes we are going to consider, it is enough to consider this effective description, but for more generic setup one should consider open quantum system and solve the system's evolution by this Lindblad master equation. For Markovian or non-Markovian processes, one can change these things. So just to elaborate upon, we have this environmental field and then photon field for the system, and when the detector acts, then there is a probability P of T1. At time T1 one can detect a photon or not. Then from the readouts, by post-processing the data, we can construct what happens to this system and construct the effective non-Hermitian Hamiltonian out of it. And this is a very nice article by Masahito Ueda from 1990s about this kind of setup. So here we are going to consider a transverse field Ising chain, where this time-dependent magnetic field is because we are pumping energy to the system, and then the measurement action, back action is taking place by this non-Hermitian parameter sitting here, which makes the Hamiltonian non-Hermitian. So this is the Pauli spin-Z operator. So this is a spin half system, and this is on-site operator, and these are pair spin flip terms. And for this time-dependent magnetic field, one can consider like a periodic drive. We are here going to consider periodic drive. It can be continuous one or discrete one. The entanglement transition we are going to describe, the qualitative features will remain same, whether we are considering this protocol or that, only the quantitative values will change. This model has a space, this model is exactly solvable. Once one map this spin half system to via Jordan-Wigner transformation to a set of spinless fermions, and then we can see that this kind of Hamiltonian can be mapped to a quadratic in terms of fermions, spinless fermions, and then one can use Fourier transformation followed by a Bogoliubov of rotation and makes the thing diagonal in Bogoliubov of quasi-particles, which are described by this, where Ck and C minus K dagger are the fermionic creation and annihilation operator in the Fourier space. So, yeah.
So this become Hermitian though, no?
No. This is for the Hermitian setup, but for non-Hermitian setup, my H is going to be complex.
Oh, I see.
Yes. And also for the Hermitian setup, this mod UK square plus mod VK square is 1, but for the non-Hermitian setup, we have to normalize things. So this is just the description of the system. Now we also have drive, so we have this H being the time dependent, so we have the instantaneous eigenvalues, and then we have to solve it in some other manner. So yeah. So first, what I'm going to consider is the dynamical signature of this kind of system.
In your previous slide, sorry, maybe I missed it, your H magnetic field will just, the eigenvalues, the eigenvectors do not depend on H, right?
What eigenvalues will?
You diagonalize your Hamiltonian very strictly,
yes.
But then the dependency on H is only in the eigenvalue and not in the eigenvector.
Yeah,
right?
it will it will be on the eigenvalues and also in the eigenvectors, because
eigenvectors also depend on H. Your eigenvectors also depend on H?
Yeah. It will depend, right? Because if we consider these two component fermionic fields, in terms of this, it is a quadratic Hamiltonian, and then this H of k is a 2 by 2 matrix. These are the Pauli matrices. And then H of t, it has some H naught plus H1 cos omega t kind of thing. Then it will depend, right, on the other parameters of the system, all the parameters, gamma and other parameters.
So tau are polymatrices here.
What?
The tau in your equation, it's a polymatrix.
Yes,
It's polymatrix.
Pauli matrices, yeah. So it will depend. Yeah, thanks. So yes. So here we will measure the system at stroboscopic times. We are going to see the observables at stroboscopic times, and what we are time evolution operator for each time period is the time ordered product of this kind of Hamiltonian evolution, and it is a time dependent Hamiltonian. And if we use continuous drive protocol, we cannot perform this time ordered product exactly. Either we have to use Trotter decomposition and compute it numerically, or we have to resort to some kind of perturbation theory. And so what we are going to discuss is, we want, because of this application of Floquet theorem, we want this to be of this form where HFK is a static Hamiltonian, and this Floquet Hamiltonian will have all the properties of the system at each stroboscopic time. So this is the, like after n stroboscopic time, the system state will have this following form, and due to the non-hermiticity, we have to normalize things so that it won't blow up and give some physical observables, appropriate physical observables. So just to set up, this is a two-level system. Suppose we compute the Floquet Hamiltonian by either numerically or perturbation theory, then at each momentum mode, it is a two-level system, effective two-level system, after it maps to non-interacting fermions. So here it is the, like any stroboscopic time, the system state will look like this, and these eigenvalues are complex now. Because of the non-hermiticity. Now depending on the sign of the imaginary part of the energy, when after normalization one branch will survive and other will go. So it will be helpful to consider what is the sign of the imaginary part in order to discuss what will be the structure of the steady state of the system in this kind of dissipative setup. Okay, so we can compute it numerically, and to compute some kind of analytical understanding of this Floquet Hamiltonian, we are going to resort to the perturbation theory, where we are going to use our drive amplitude as the largest parameter of the system. It is larger than other parameters of the system, and then we are going to compute the Floquet Hamiltonian order by order as like power of 1 over h1. Yeah.
Now, go back to where you were. You've got on the bottom left, you've got the K to a steady value.
Yes, yes. So these are the correlation functions. Yeah, because there is. Yeah.
What's the Hermitian conjugate doing in the next to it?
Next to it, it keeps on oscillating.
Yeah, this is just C minus K, CK. The Hermitian conjugate.
So one is decay, the total is oscillating.
One is decay and other is oscillating. Yes, yes. Yeah, yeah. Yeah, so we can construct the effective Floquet Hamiltonian by perturbation theory, considering this as the 0th order Hamiltonian and this as a perturbative part, and this is same as the time dependent perturbation theory interaction picture, but in a rotating frame. So when we compute the first order Floquet Hamiltonian, so we are here just seeing the structure for each momentum mode, because all the other things are same, other momentum modes. So here for each momentum mode, it is a 2 by 2 matrix, and one can see at the off diagonal there is a Bessel 0 sitting here. So if I fix other parameter of the system and varying the frequency, then what will happen, that at the frequencies where this 0th order Bessel function vanishes, one have an emergent conservation. It's a magnetization, it will be emergent conservation here, and okay, sorry. So this will be, and if you see this model Hamiltonian, if it is static, there is no magnetization conservation there because of this pair spin flip turn. But this is emergent, and this will be approximate because if you compute the second order Floquet Hamiltonian, then all the other Bessel function will start appearing, and then this will be approximate, but this term will be suppressed by 1 over frequency. So if we are in the high frequency regime, we can approximate our we can understand it using only the first order Floquet Hamiltonian. So, okay, so here we can compute the steady state, as I have mentioned, the late time state, infinite time state. It depends on the sign of the imaginary part of the energy. So here what we will going to focus is to compute the entanglement properties of this steady state as a function of this measurement rate and the driving frequency. So first I will define what do we mean by entanglement entropy. Suppose I have a chain, I divide it into two parts, and such that the Hilbert space of the total system is the direct product of Hilbert space of part A and part A bar, and then one can compute the reduced density matrix by tracing over the degrees of freedom of one of the subsystems and compute the von Neumann entanglement entropy, which essentially gives you the information about the quantum correlations which is shared between two parts of a system by a particular quantum state. And we are going to replace this state psi by the steady state of our model Hamiltonian and see what kind of entanglement properties it has. So just I'm going to give a 2-qubit example. So it is you have this 4 state, it is a Hilbert space of 4-dimensional Hilbert space, and if you consider qubit 1 as subsystem A and qubit 2 as subsystem A bar and want to compute what is the entanglement shared between A and A bar of this particular state, down down and up up, and you can compute the von Neumann entanglement entropy, it will be log 2. And this is the maximally entangled state for this 2-qubit system. So, okay, then we are going to replace psi by our steady state and see what happens. So, see, the thing is, if you compute to compute the entanglement entropy, you have to diagonalize this 2 to the power L cross 2 to the power L matrices. And when you are trying to compute this thing in the thermodynamic limit and increase your subsystem size, it is very costly numerically to compute this type of eigenvalues. So, what happens that in case of this type of integrable system where it maps to non-interacting fermions, special tool exists to find the spectrum of rho A, where you need to diagonalize only a matrix of polynomial size. So this is the matrix. It is a correlation matrix of this kind of Hamiltonian, and this correlation matrix is essentially in each of these rows and column, it is a 2x2 block. And it comes from the Gaussianity of our state because it depends only on these correlation functions. So if for each momentum mode we can compute this correlation function, we can compute a 2x2 matrix, and then we can Fourier transform it, and this is the pi L, and pi steady k dot sigma k is just pi x sigma x, pi y sigma y, and pi z sigma z. So here this expectation value will be taken with respect to the steady state of the system. Okay, so here we can see that this is a block Toeplitz matrix, and as the rows, all the rows have the same entries, and this one can use the asymptotics of block Toeplitz matrix in order to compute this entanglement entropy. And just to mention how the reduced density matrix eigenvalues are related with the eigenvalues of this particular matrix is, if nu j is the spectrum of this matrix, this is a 12x12 matrix, and we have the spectral reflection symmetry. For each nu j we have a minus nu j pair, and from this one can compute the spectrum of rho L by taking this kind of combination where xj can take values 0 and 1. So from this you can compute a 2 to the power L eigenvalues of the system. Okay, So first, I'm just going to describe that this entanglement entropy, here I am exploited the structure of this spectral reflection symmetry of the matrix and write down the entanglement entropy in this form. Then using Cauchy's residue theorem, you can convert this as a determinant, logarithm of determinant of a Toeplitz block Toeplitz matrix related with this correlation matrix, this particular correlation matrix in this manner. Okay, sorry. So this is the generator and we have, so this is the main phase diagram, entanglement phase diagram. Here what we have done is we have computed the entanglement entropy for a steady state for a subsystem size. Then we vary the subsystem size and see how the entanglement entropy scales. And then this is just alpha log L plus beta. So we have a logarithmic law here and a area law there. So this is a logarithmic to area law transition. This rate curve is from the numerical computation of the phase boundary and the green one is from the analytical curve. And how do we, if we see the structure of the 2-point correlation function, in the logarithmic scaling it has a jump singularity, and in the area law scaling it is a smooth function in the momentum space. And and one can expand like one can show from the Szego-Wiedemann-Strong limit theorem of the determinant of Toeplitz matrices that when the generator of such Toeplitz matrix has a smooth structure of the smooth structure over the momentum space here for the momentum space, this volume law scaling, the coefficient will vanish. And also the logarithm law will vanish and we will have this area law. And it is not applicable for the symbols which has this singular nature. So for that we have to use Fischer-Hartwig conjecture. So here we have expanded it. So this is the numerical curve and then we are approximating is with this green curve and by expanding around these singular points, and we have additional singularities at 2 pi and 0, and we are going to remove this and see what is the coefficient of the logarithmic scaling. So this is the sine function after expanding, and in the limit when we have this our measurement rate is much lower, we can use this block Toeplitz matrix as a Toeplitz matrix times a constant matrix, and we can perform Fischer-Hartwig conjecture over the generator of these Toeplitz matrices. And so this is the Fischer-Hartwig conjecture, where if you have root singularities and jump singularities, one can write down the generator in this form. And we have applied this Fischer-Hartwig conjecture, compute the determinant, log determinant of this Toeplitz matrices. We can see this will go to 0 by contour integration, and this will be there. We can compute this term, and this is the result. This rate points is the numerical curve. This is the coefficient of the log term. This blue one is from the Floquet perturbation theory, and from the Fischer-Hartwig conjecture we can correctly predict the transition point here. So, this is what I want to explain here. In the low frequency regime you can have entanglement crossover, and this can be traced back to the effective long range nature of the Floquet Hamiltonian, and that's all. That's what I want to say in this talk. So we have entanglement transitions and we can explain it analytically also. That's all.
Okay, thank you.
Yeah.